Jai Hind everyone. I am Shruti Jain, Assistant Professor MCA Department from Ajay Kumar Garg Engineering College, Ghaziabad. The topic that I am going to talk about is the classical problems of synchronization using semaphores. The subject related to it is operating system. The subject code is KCA 203 and this is mainly for the MCA students of second semester. So whenever we are starting with how the problem is to be synchronized, we first talk about the critical section problem. So now what a critical section problem is, suppose we have around n processes or maybe many processes that are coming into the system. So the system consists of suppose n processes which range from P0 to Pn-1. Then each of the process has a segment of code that is known as a critical section, where the process would be changing common variables, updating a table, or whatever execution the process has to do. That process is to be done into the critical section of the process. So whenever a process executes a code which needs to manipulate any shared data or a resource, then the process enters into the critical section. Now the important feature is that this critical section offers a situation or a condition of mutual exclusion. Now mutual exclusion says that at a time only one process can enter into the critical section. If many processes are there, then out of those many processes only one process will be entering into the critical section doing the execution. Once that process comes out of the critical section, only then the other process will enter into the critical section. So here a section of a code that is implementing the request to enter into the critical section is known as the entry section. So if we look the pseudocode over here, we have for every process we have a critical section, we have the entry section, we have the critical section, then we have the exit section and the remainder section. So here what happens is when a process enters into the entry section, it checks whether it is eligible to enter into the critical section or not. If the process is eligible, then it enters into the critical section, do the execution, performs the execution, enters into the exit section, and if something is left to be executed which does not need any cooperation of any other process or the resource, then it enters into the remainder section and exits. Now we have multiple solutions to the critical section problem. The first one talks about the mutual exclusion, which we just discussed, that mutual exclusion is a property where no other process can be executing in their critical section. That is, one process at a time can enter into the mutual exclusion, can enter into the critical section and can perform its execution. The next one, the progress, that is, if no process is executing in its critical section and some process wish to enter into the critical section, then only those processes which are not executing in their remainder section can enter into the critical section and then do their execution. Bounded waiting, there is a limit or the number of times that the processes are allowed to enter into the critical section. That it should not be the case that if one process has entered into the critical section, it can again enter into the critical section without any reason. So there is a time limit or there is a number of limit on the number of times a process can enter into the critical section. Coming to semaphores, the semaphores are the integer variables that are primarily used to solve the critical section problem. Here we have, it can be a combination of two atomic procedures, that is the wait and the signal. So coming to wait, we have suppose a process that is entering into the wait section. Whenever the value of the process is less than equal to 0, it will wait over here. And once it exits, it will decrease the value of the semaphore and then it will move out of the section. We have a signal section wherein when a semaphore is entering, this S is a semaphore which is entering into the section. The work of the signal is to increment the value of the semaphore by 1. Now we have two types of semaphores. The first one is the counting semaphore and the other one is the binary semaphore, which works on only two values, that is 0 and 1. The binary semaphore is also known as a mutex lock. Now we can implement a counting semaphore by using the binary semaphore, which provides the concept of mutual exclusion. We have a section over here where we have a semaphore S whose value is initially 1 and we have different processes that are PIs. So when a process enters into it, it will wait for the semaphore to execute. Then only one process will enter into the critical section. Once that process enters into the critical section, the value of the semaphore is decremented, because we have seen the wait section always decrements the value of the semaphore by 1. The process which tells the other processes that there is a process which has already entered into the critical section. Until and unless the semaphore value is incremented, no other process can enter into the critical section. The process which entered into the critical section over here will perform the execution. Once the execution is done, then when it is exiting from the critical section, it will again increment the value of semaphore by 1, so that the other process who wish to enter can enter into the critical section. Then the process will enter into the remainder section and will exit. So now we are going to discuss the 3 main problems of synchronization, the solutions for them: the bounded buffer problem, reader's writer problem, and the dining philosopher problem. So coming to bounded buffer problem, the bounded buffer problem, which is also known as the producer consumer problem, it is a classical problem of synchronization, where we have a single buffer of n slots where the producer is producing and the consumer is consuming from the same buffer. Now the problem here is the producer and the consumer cannot produce and consume at the same time. So we need to check when a producer is producing an item, the consumer do not consume that item. The second thing is the producer can only produce an item when there is an empty slot in this buffer. If the buffer is already full, then the producer cannot produce an item. Similarly, the consumer will consume the item only if there is one element, a minimum of or at least one element into the buffer. If the buffer is empty, the consumer cannot consume any of the item. So if we look at the pseudocode, what happens? It waits on the empty. That means when the producer, this pseudocode is related to the producer function where the producer wants to produce an item. So when the producer is entering into the system, it will wait until the value of empty is greater than 0. If the value of empty is greater than 0, then it will wait and then it will decrement the value of empty by putting a wait semaphore onto the empty over here. As soon as it puts a wait on the empty, it will acquire a lock on this. The mutex is a lock which is being kept just to tell other processes that they cannot enter into the critical section. So this producer enters into the critical section. It performs the insertion operation. It produces an item. Once the item is produced, it will release a lock by keeping a signal to mutex, that is incrementing the value of mutex by 1. Then it will signal full, it will increment the value in full just to tell that an item has been updated, an item has been added into the buffer, and then it will exit. Now the work of the producer was to increase one item into the empty slot. So it has decreased, to add an element into the full slot. So it will decrease the value of empty because now one element in the full has been added and empty block has been subtracted. Now we look at the consumer function over here. The consumer will put a wait until the value of full is greater than 0 because it has to decrement the value of full as the consumer is consuming an item. So it will put a wait onto the full and it will acquire a lock onto the lock. Here is a mutex variable again, so it will put a wait onto the mutex so that no other process can enter into the critical section. The consumer will remove an item, that is, it will consume an item. Once that operation has been performed, it will release a lock by keeping a signal onto the mutex by increasing the value of mutex again by 1. It will increment the value of empty by putting a signal onto the empty because now since one element has been consumed, the value of empty will be incremented. After consumption, it will move out of the block. The next problem that we are going to discuss is a reader's writer problem where multiple readers can enter into the critical section, but only one writer is available to write onto the critical section. So when a writer is into the critical section, no other reader or writer can enter into the critical section. But yes, when a reader is performing a reading operation, then multiple readers can perform the reading operation or can enter into the critical section, but only one writer can enter into the critical section. The priority of the reader over here is higher because we have multiple processes which need the resources to be read, can enter into the critical section and do their execution. So here we have a shared resource that should be accessed by multiple processes. So we have two types of processes over here, that are the reader and the writer. Any number of readers can read from the shared resource, but only one writer can write to the shared resource. So if we look at the code of the writer's process, the writer will put a weight onto the W. The writer will perform the write operation, whatever operation needs to be done, and then once it is exiting, it will put a signal onto the write operation. Now if we look at the reader's code over here, so here when the reader is entering, the first reader is entering, it will put a weight onto the mutex, it will put a lock and will increase the read count, because here the multiple readers can enter into the reading section. So now suppose initially the value of read count was 0. As soon as the first reader enters, the value of read count increases to 1. Now when the value of read count increases to 1, it will put a weight onto the W so that no other writer can enter into the critical section till the time the readers are there into the reading section. It will put a signal to M to allow other readers who wish to enter into the reading section. But this check will only be performed for the first reader who is entering into the critical section. Because once the wait for writers has been performed, no other writer now can enter into the reading section, but multiple readers can enter. So once all the readers have entered, or once the readers are entering into the system, they will perform the reading operation where there are multiple readers. Now again, when the reader wants to exit, we should understand that only a reader can either enter into the critical section or it can exit. Both entry and exit is not possible at the same time. So once the reader wants to exit from the critical section, it will again put a weight onto the mutex. The value of read count will be decremented, and if we have the last reader who is exiting, it will give a signal to the W to allow any writer to enter into the critical section, because now we have the last reader who was there into the reading section. Once that reader exits from the reading section, it will put a signal onto the W to allow all the writers to enter, and it will again release the lock that it has acquired while he was exiting from the critical section. So this was related to reader's writer problem, where we had only one write operation to be performed, but multiple processes can run into the critical section while they are performing the reading operation or while they are using any of the shareable resource. The last problem that we are discussing is the dining philosopher's problem. The dining philosopher's problem says that here suppose we have 5 philosophers who are sitting on a dining table in a circular motion, and we have 5 chopsticks, that are 5 resources that can be accessed by each of the philosopher. Now each philosopher will be in either of the two state. He could be either in the thinking state or he could be either in the eating state. When any of the philosopher is in the thinking state, at that time he will not be using any of the chopsticks over here. But as soon as the philosopher thinks of entering into the eating state, he will first pick up the left chopstick that he has. Then if that is available, he will pick up the right chopstick that is available, and then it will start eating it will start accessing the resources. So each and every process has to check. These philosophers are basically the processes who are entering just to who are entering for the execution. So every process should hold the two of the resources, the left resource and the right resource. in order to perform the execution. So at any instant, a philosopher is either into the eating or the thinking state. When a philosopher wants to eat, he uses two chopsticks, one from their left and one from their right. So now when a philosopher wants to think, he keeps down both the chopsticks at their original place. Now we have a problem over here. Suppose the philosopher is into the indefinite thinking. That means the philosopher is not using any of the resource. So here we put a time limit that the process or the philosopher cannot enter into the indefinite thinking. The cycle of the philosopher, it should be in such a way that he is either in the thinking or the eating state, and he has to enter into the eating state at some point of time. So if we look at the code of the philosopher over here, we have, when the philosopher is entering, he will wait for the chopstick or the stick I. Suppose we are working with the philosopher P1. So the left chopstick for P1 would be the first chopstick and the right one would be the chopstick 2. So the first philosopher who is putting a weight onto the stick I, that means he wants to acquire the left chopstick over here. Then when he is waiting for the next one, he will be using the formula stick I plus 1 modulus 5. We will discuss the formula in quite some time, why we are using this modulo. So this one is I, that is the value of I is 1 over here, because we are discussing it for the process P1. 1 plus 1 is 2, modulus 2 will give us the value as 2. So now he is putting or acquiring a weight onto the second chopstick, that he has acquired these two chopsticks. Now no other process can use these two chopsticks until this P1 releases these sticks. Now the philosopher will perform the eat operation. Once that eat operation is performed, it will leave the left chopstick first and then the right chopstick. Now why are we using this formula, the modulo 1? Suppose we are working on the fifth process. Now when the fifth process enters, it will put a weight again onto the stick I, that is the fifth chopstick. But now because it needs to put a weight onto the P0, that is the 0th chopstick, what it will do, it would be the first one. So it would be 5 plus 1, that is the value 6 modulo 5, it will leave us the remainder as 1. So because here the philosophers are sitting into the circular motion, so if we have the P1, P2, P3, P4 and P5, so P5 would need this P5 and the P1 chopstick if the philosopher wants to perform the eat operation. So now here a problem exists. Suppose if we talk about this problem over here, now all the processes wants to enter into the eating state at a one go, and they start accessing their left chopstick. Now each and every process will be holding their left chopstick and no process will be left with the right chopstick. That means here we have a situation where no process will be able to acquire both the chopsticks, and hence we can have a possibility of deadlock. Now deadlock is a situation where the processes are accessing some of the resources but are waiting for the other resources. Those resources are already held by some other resource. So no process is able to do the execution. So in that case, the possible solution is we can allow only 4 of the philosophers to sit in the table. So in that case, what will happen? Suppose we have P1, P2, P3 and P4, but we have the 5 chopsticks over here. So even if each of the process is accessing the left of their chopsticks, we still will be left with one of the chopstick which can be acquired by P4. When the P4 performs the eat operation, it will release the 2. This can be acquired by P3. Once it performs the eat operation, this will be released and will be acquired by P2. and hence the deadlock situation will never arise. So this deadlock situation is a situation which we do not want any of the process to enter into. Hence, we always try to work with the solution with the 4 philosophers. That's all for today. Thank you.